In this video, we're going to look at a type of problem called a gravimetric analysis problem. And all of the problems that we're going to talk about in the next few videos, gravimetric analysis, volumetric analysis, and titrations, they all fall into this broader category of what we call quantitative analysis problems. And what this is going to boil down to is it's going to basically boil down to this idea of determining some kind of information about an ion or a molecule in solution. So we're going to do something in order to figure out the concentration of an ion in solution. So, for example, the first one we have is gravimetric analysis, and in this one, this is going to involve forming a precipitate. So you form a precipitate, and then you use the mass of the precipitate to determine the concentration of an ion in solution. So we're going to actually take a look at a problem in just a second where we do this. We're going to take a look at two problems where we do this. But for example, in the first problem, what you're going to see is basically they want to figure out in the first problem the concentration of lead in solution. So what they do is they take a solution and they precipitate lead with bromide and they form a solid precipitate of lead bromide. And from this solid precipitate of lead bromide, the lead that's built up into this, we can calculate using the number of moles to go back and determine how many moles of lead 2+ were in solution. And if we know the volume, we can get the concentration. So that's the idea behind gravimetric analysis. You form some kind of precipitate, and then you work your way back to figure out the concentration of an ion in that precipitate in solution. So let's take a look at that practice problem. In lecture problem 4, we have two examples of these gravimetric analysis problems. So the first one, as I said, it says a company produces automotive components and is suspected of contaminating a river with lead nitrate. The EPA collects a 1.23 liter sample of the river water and adds sodium bromide to fully precipitate the lead ions and recovers 22.57 grams of solid. Calculate the molarity of lead 2+ in the water. So if we want to get the molarity of lead, and one way that you can summarize molarity is by putting whatever it is that you want in brackets like this, and then we can say, well, in order to get the molarity of that, well, we need the moles of lead 2+ divided by the volume of the solution, and we have the volume of the solution already, so that's 1.23 liters. So now the question is how do we get the moles of lead that are in that solution? So we have to do stoichiometry. So it says we get 22.57 grams of the solid, and to figure out what solid we're making, we have to write the balanced reaction. So in this case, we have lead nitrate, which is what they suspect they're contaminating the river with, and we're reacting this with sodium bromide. So we have to predict our products. So we do our partner exchange. So we're going to get lead bromide, and we put a 2 down below because the lead is a 2+. And when we check our solubility rules, we're going to see that lead bromide is a solid, and then we're going to get sodium nitrate. And this, checking our solubility rules, that's an aqueous. So to balance this, we have to put 2 in front of the sodium bromide, and we have to put 2 in front of the sodium nitrate. So in order to work this out, what we're going to do is we have to figure out how much lead was in that lead bromide to work back and figure out the concentration of lead nitrate. Okay, so what we're going to do is we're going to take this, we got to figure out the molecular weight of this because this is the lead bromide. So we need to get the molecular weight of lead bromide, and if you calculate, add up the lead and the 2 bromides on the periodic table, you're going to get 367.01 grams of the lead bromide for every 1 mole of lead bromide. And then according to our balanced reaction, for every 1 mole of lead bromide, there is 1 mole of lead nitrate or 1 mole of lead ions. Because remember, this is solubilized and it's aqueous, so really this is Pb2+ in solution plus 2 NO3- in solution. So we can say for every 1 mole of PbBr2, there is 1 mole of Pb2+ in solution. And so now we can calculate our number of moles. And in this case, we get 0.061496 moles of the lead 2+. And we can plug that into our molarity calculation. And when we divide 0.061496 by 1.23, we get a concentration of lead 2+ that's equal to 0.0500 molar. So that's how we work that problem. Okay, so let's take a look at the second problem. This one's a little bit more challenging. So the second problem says limestone contains mostly calcium carbonate. You dissolve a 128.3 milligram sample of limestone in HCl according to reaction 1 and precipitate the calcium 2+ ion with a solution of sodium oxalate according to reaction 2. Calculate the percentage of calcium in the limestone if 140.2 milligrams of precipitate are formed. So in essence, what this problem is telling us is that we've got a sample of some limestone, and that limestone is equal to 128.3 milligrams. So they dissolve it in HCl according to reaction 1. They precipitate the calcium ion with the oxalate according to reaction 2. Then they tell us we get the 140.2 milligrams of precipitate, so that's this calcium oxalate down here. So I'm just going to write that we get 140.2 milligrams of the calcium oxalate down there. And what the problem is asking us is it's saying, well, okay, what is the percent of calcium in the limestone? So in order to do this, we're going to need the mass of calcium divided by the mass of limestone times 100. And so we have the mass of the limestone from the problem. So that's going to be 128.3 milligrams. And if you want, you can convert that to grams. It doesn't really make a difference. We're gonna keep it in milligrams for the sake of this. So that's the question. The question is now what we need to get that mass of calcium. And we're going to get that mass of calcium by figuring out how much calcium is in that calcium oxalate. So if you take 140.2 milligrams of the calcium oxalate, and we want to figure out how much calcium is built into that, well, first thing we have to do is we have to get this into grams, because we need to use the molecular weight to get to moles. So we're going to first divide this by, we're going to say for every 1,000 milligrams there's 1 gram, and then that gets us into grams. And then we have to come up with the molecular weight for the calcium oxalate. So on an exam, we would probably give this to you, but for the sake of this question, we're going to have you calculate it. So if you were to calculate the calcium, the 2 carbons, and the 4 oxygens, you would get 128.1 grams of calcium oxalate for every 1 mole of calcium oxalate. And what the problem wants us to do is we got to now go from moles of calcium oxalate to moles of calcium. For every 1 mole of the calcium oxalate, we have 1 mole of calcium, right? So built into this calcium oxalate is 1 mole of the calcium. What we're going to do is to get the mass, we can say, well, for every 1 mole of calcium, we can look up the molecular weight on the table. It is 40.08 grams. And then we're going to convert this to milligrams. So for every 1 gram, there's 1,000 milligrams. And finally, we're going to come out with 43.86 milligrams of the calcium 2+. So like I said, with gravimetric analysis, we do some kind of precipitation, and then we work back to figure out an ion that was originally in the solution. So we place our 43.86 milligrams over our 128.3 milligrams, and then we multiply that by 100. So our percent calcium, I'm just going to move this down here, our percent calcium is going to equal 34.19%. So these are 2 examples of gravimetric analysis problems. And in the next video, we're going to take a look at volumetric analysis, which involves 2 basic classes. We can either have a volumetric analysis where we do some kind of precipitation, or we can do a volumetric analysis where we do some kind of neutralization reaction. And those tend to be called titrations.